Welcome viewers to the third segment of the fifth lecture for the online series of lectures for the course of Dynamical Systems. Towards the end of the second segment, we were discussing limit cycles, and we have shown in a certain example, which we call example 2, that 0, 0 is the only equilibrium point of that system. So we have also said towards the end that for that system we would like to prove the following, that for mu negative, strictly negative, if the point PQ lies in the ball of radius 1 centered at the origin, set minus the origin, then the omega limit set of the orbit of P, Q, then the omega limit set of the orbit through PQ is just the origin. Okay, this is what we want to prove. So we'll proceed as we did in the case of negative gradient flows by considering a function, a scalar function, v from R2 to R, given by v of x, y is equal to x squared plus y squared. So we pick up a point from R2, say this ordered pair x comma y, and take the norm squared, and that is going to be the value in R, or the image of x comma y under the map V. Okay. So we'll take this scalar function and first show that if P comma Q is in this B1 0, 0 set minus the origin, if PQ lies in this set, then V of the solution PPQT, okay, because UPQ at T is going to be a vector in R2, right? And V of UPQ at T will decrease with increasing time. In other words, V decreases along the orbit. Gamma P comma Q. This is what we need to prove first. Okay, so it is worth mentioning here that the function, this function U sub P comma Q is a map from J sub P comma Q, which is the maximum interval of existence for the underlying solution of the system that we are considering in this example 2, to R2, denote the solution of the system in equation number 22, subject to the following initial condition. Okay. So let me write down equation number 22 from the previous segment first. So it was dx over dt is equal to minus y plus mu x times 1 minus x squared minus y squared, first equation. The second ODE was dy over dt is equal to x plus mu y times 1 minus x squared minus y squared. Okay. And the initial condition was as follows: u sub p comma q at the time 0 is p comma q. Okay, we call it 26. The initial condition we numbered by 26. Okay, so this is the setting. Okay, so we need to mention here that J sub p comma q is the maximum interval of existence. Of the unit solution is the maximal interval of existence of the unit solution. Okay, good. Let me erase this top part, create some room, and now here we denote see that u sub p comma q at t is a vector in R2, and we denote it by x of t comma y of t. So it's a vector with x component and y components. X component given by x of t and y component given by y of t. You see that each of the two components vary with time. So the x component and the y component of this solution at time t varies according to this system. Okay, subject to this initial condition. Good. So, according to the definition of the scalar function, v of u sub p comma q at t is going to be v of xt comma yt, right? Which according to the definition of v is going to be xt squared plus y of t squared, right? So in order to show that v of u sub p comma q at t decreases with increasing t. Increasing t, first compute this derivative, the time derivative of this function. Which is the dot product of these two vectors, gradient of v at u sub p comma q at t dot the time derivative of the solution u prime sub p comma q at t. It's just the plain use of chain rule, where this time derivative of the solution is nothing but, as we have denoted, we had designated this solution, time dependent solution, as this time dependent order pair. Then its derivative is going to be dx over dt at time t and dy over dt at time t. Good. That one can obtain using this system 22. Okay. And this is going to be equal to, so the gradient of v has two components as usual, because it's a vector in R2. Whose components are, no, since this is x squared plus y squared, the x component is simply 2x and the y component is 2y. So 2x gets multiplied with this component of this time derivative of the time dependent solution, from which it follows that this is 2x times minus y plus mu x times 1 minus x squared minus y squared, and 2y times x plus mu y times 1 minus x squared minus y squared. So if we just do some algebraic manipulation, we see that this 2xy cancels against this 2xy, and finally we have 2 mu x squared 2 mu x squared times 1 minus x squared minus y squared plus 2 mu y squared times 1 minus x squared minus y squared, resulting in the following: 2 mu times x squared plus y squared times 1 minus x squared minus y squared, right? So see that I have suppressed the time dependence here. This is actually, this guy is actually 2 mu times x of t, squared plus y of t squared, and this is nothing but 1 minus x of t squared minus y of t squared. Okay, good. So what we have finally is the following. So let me erase this bottom part now. So let me write it again. 2 mu well, it's already written there. I don't have to write anything else. Okay, good. So we therefore have that d dt v of u sub p comma q at t is going to be equal to 2 mu times, this is nothing but v of u sub p comma q at t times 1 minus, this is again the same thing, v of u sub p comma q of t. This is our equation number 27. Okay. Now, for our convenience, we are going to express this guy as small v as a function of time. Okay. So v of t is going to be equal to big V, this is small v, of u sub p comma q of time. Okay. For all t in this maximal interval of existence, right? So with the help of this new function, small v, which is the composition of these two functions, we can rewrite equation 27 as dv over dt is going to be equal to 2 mu times v times 1 minus v. This is our equation number 28. Okay. Okay. So now remember the hypothesis in that what we were given. We were given that the initial vector belongs to this set, right? The ball of radius 1 about the center set minus this origin. And this function small v of t is this, right? So small v at time 0 is, according to this definition, big V of u sub pq at 0, right? Which is nothing but big V of p comma q, which is equal to p squared plus q squared. And since p comma q belongs to this set, according to the hypothesis, p squared plus q squared will be strictly less than 1, right? And since PQ is not the origin, it is strictly greater than 0. Okay? And P square plus Q square is nothing but small v of 0, from which we see that this is synonymous to this strict inequality, right? So when mu is strictly negative and this is given, so from the right side we see that from the right side of equation 28 we see that dv over dt is strictly negative. Okay, so thus if this vector p comma q belongs to okay, so I have already said it, so I don't want to repeat it. And so this is good. It is strictly negative. Now there is a few other things that we want to discuss. V of u sub p comma q at t is, according to the definition of this function, big V, this is xt squared plus yt squared, okay? And this is nothing but the norm of this solution at time t, right? U sub p comma q at t, the norm of this guy's squared, the square of the norm of the solution. Why this is the case? Since u sub p comma q at t is this ordered pair, right? With components xt and yt. Okay. So remember that we have written small v as a composition of these two functions, big V and small u. Since small v is strictly decreasing with time, so is big V, right? Because small v, so, well, what I mean is that not big V, big V composed with this this function u. So that's what I'm writing here. Big V of up comma q at t is equal to the square of the norm of u sub p comma q at t decreases with increasing time. With increasing time. Okay, good. Okay. Where is this now? Okay, since v as a function of time is decreasing with increasing time, for positivity, strictly positivity, one must have v of t is less than v of 0, which implies that big V of u sub p comma q at t is less than big V of u sub p comma q at 0, implying the square of the norm of u sub p comma q is less than the square of the norm of p comma q, but the square of the norm of p comma q is, by assumption, less than 1. Okay, so now what's happening around? To summarize, for mu strictly negative, if this vector p comma q belongs to this set B1, 0, 0, set minus origin, that is, in terms of this function small v, it tells us that v of 0 is between 0 and 1. Then if this is the case, then v of t is strictly less than v of 0, and we already know that v of 0 is less than 1. Okay, for all positive t, right? Because things start happening from t equal to 0. That's the initial point. Okay, from which we get that the solution u sub p comma q at t is in, because of this inequality, belongs to this open ball, right? Because v of t is strictly less than 1. Okay. So that will belong to this open ball for all t in this maximal interval of existence intersecting with 0 infinity. Okay. Okay, so this is going to be our equation number 29. So let me erase this top part. Now, using the same argument as we did in proving part D of negative gradient flows, one shows that now using the same argument as we did in proving part D of negative gradient flows, one shows that u sub p comma q at t is defined for all t positive, right, with the help of escape in finite time theorem. Escape in finite time theorem. Okay, which means that we prove that this guy is simply zero infinity. Okay. Now, but the set of all solutions u sub p comma q at t for all t in this interval, half open interval, or t greater than or equal to 0, constitute the forward semi-orbit, right? The forward semi-orbit gamma plus p comma q. Hence we have shown that gamma plus p comma q is contained in this ball, right, of radius 1 centered at the origin. Okay. So if you want to draw a picture, then try drawing this ball first, which is B1 0, 0. This is the origin 0, 0. And now see that at initial time, if you are at a point here which is strictly inside the open ball that we are considering, then as time progresses, the trajectory will spiral inside the ball, and will be attracted to the origin as time progresses, right? And will be attracted to the origin as time progresses, meaning that the norm of the solution will decrease over time, right? So the norm of the solution will decrease over time. Okay, so this is a picture that reflects what's happening. Okay. So now let me erase this bottom part. Now it then follows, given this thing, it then follows from the result of proposition 2 of lecture 4 that the omega limit set of the underlying orbit is non-empty. And one can also show that the omega limit set is actually contained inside the compact set that contains this forward semi-orbit. The compact set being this, the closure of the underlying open ball centered at the region of radius r. Okay, so the next goal would be to show that the next goal would be to show that the omega limit set of the orbit through PQ is the origin. For all PQ in this open ball. Okay, this is what we want to show. Okay. Okay, so let me erase everything. So remember equation 28 when after we introduced the function small v, we had this equation dv over dt equal to 2 mu times v times 1 minus v. That was our equation 28. Okay. So by separation of variable and partial fractions, we obtain from this expression the following: dv over v times 1 minus v is going to be equal to 2 mu dt. Then we integrate on both sides and use partial fraction on the left hand side to obtain the following: integration of 1 over v plus 1 over 1 minus v dv is equal to integration of 2 mu dt, and then I have ln v minus ln 1 minus v to be equal to 2 mu t plus k, where k is the integration constant, and this can be written down as ln v over 1 minus v equal to 2 mu t plus k, and this translates to v over 1 minus v equal to some other constant c e to the, which is relative to k. I'll let you calculate it. Very easy exercise. E to the 2 times mu t, where we find this constant, right? Now, just plugging in t to be 0, we see that this constant is nothing but a v at time 0 divided by 1 minus v at time 0. Okay, so therefore, v over 1 minus v is v at 0 over 1 minus v at 0. These are all small v. E to the 2 mu t, from which it follows that v of t is equal to, so if I write v of 0 as v sub 0, then we see that this is v sub 0 e to the 2 mu t over 1 minus v sub 0 plus v sub 0 e to the 2 mu t for all positive time, right? And this makes sense as long as v sub 0 is strictly less than 1. Because if t approaches infinity and positive infinity, since mu is negative, well, that's fine. see that. Yes, you want v of 0 to be between 0 and 1, right? Okay. So this is our equation number 30. Now we see from equation 30 that if P comma Q is in this open ball and mu is negative, mu is strictly negative, then why do we want this to be strictly less than 1? You see that if t approaches infinity, if this were equal to 1, well, sorry, if this were equal to 0, then it would become 0 over 0. That's what we don't want, okay? So if this holds and mu is strictly negative, then the following limiting expression holds, which is the limiting expression of v of t as t approaches infinity is just 0, because this is non-zero, it's a non-zero number, and this is going to be 0 and this is going to be 0 as t approaches infinity, because mu is strictly negative. Or, so written in terms of big V, this reads big V of u sub p comma q at t is 0. But notice that u sub p comma q at t is nothing. From the definition of flow, it's going to be theta t comma p comma q, right? And big V of u sub p comma q at t is equal to the square of the norm of this solution vector, right? Which is the norm of theta t comma p comma q, the square of this norm. Okay. So therefore, we see that the limit of this die as t approaches infinity is equal to 0 implies the limit of the norm approaching 0 as t approaches infinity. Whenever the vector p comma q is inside this open ball of radius 1 centered at the origin. This is our equation number 31. Excuse me. Okay. Now, assume that, which we already did, p comma q is in B100, and this is a point x bar y bar in this omega limit set of the orbit of this PQ. Okay. Then Then by the definition of omega limit set, then by the definition of omega limit set, there exists a sequence of positive real numbers Tm such that Tm approaches infinity as m approaches infinity, and the limiting expression of theta Tm comma p comma q is just the ordered pair x bar y bar as m approaches infinity. It follows from the definition of omega limits. This is our equation number 32. Well, this was 31, right? Part of which has been erased. So this was 31. Now, but from 31 and from continuity of norm, one already knows that the norm of this vector x bar y bar is equal to the norm of, let us replace x bar y bar with this limiting expression from 32, and I can take the limit outside as norm is continuous, like I said here. Okay? I'm taking this limit outside of the norm using the continuity of norm, and from 31 we know that this is 0, right? So we have been able to prove that the norm of this vector is 0, and we know from the property of norm that the only vector that has norm 0 is the 0 vector. So which proves that this vector x bar y bar is the 0 vector. Well, then we have the result that the omega limit set of the orbit of the point p comma q is just the origin for all pq lying inside this ball B100. This is our equation number 33. Okay. Okay. Now let us erase everything and divert our attention to a different direction. One can go on to show that S1, which stands for the unit circle at 0, 0, one can go on to show that S1 is an orbit of a point PQ, P comma Q, with P square plus Q square is equal to 1. So meaning that, let me draw a picture for you here. If I take this unit circle, which is the circle of radius 1 centered at this point 0, 0, this is S1. So it is actually the orbit of a point lying on this circle. So if I choose any point on this circle denoted by p comma q, such that p square plus q square is equal to 1, and then compute the orbit of this point, that is actually going to be the same circle. Okay. This is what's written down here. Now assume p comma q being on this circle S1, which is nothing but the boundary of this open ball B100, and that u sub p comma q from j sub p comma q to R2 is the unique solution to the system in equation number 22. What was equation number 22? The system that we are discussing, right? dx over dt is equal to, let me write it for you so that you can keep track of everything. Dx over dt is minus y plus mu x times 1 minus x square minus y square, and dy over dt is equal to x plus mu y times 1 minus x square minus y square. This was 22. Okay. And subject to the initial condition, this is the system, subject to the initial condition, x at 0 is p, this x at the initial time is p, and y at the initial time is q. This was our equation. This is our equation number 34, where we want p comma q to lie on this circle. So where p square plus q square is equal to 1. So then there exists this angle phi 0 in this half open interval 0 to 2 pi, such that p is equal to cosine phi 0 and q is equal to sine phi 0. Why? In that case, p square plus q square will be equal to 1. And this equation will be fulfilled. Right? We show that at a subsequent time, the solution is going to be equal to cosine t plus phi 0, comma sine t plus phi 0 for all t in the positive real axis. Should be r plus. Okay. So this is our equation number 36. That was 35. This is 35. And this is equation number 36. Right? Now put w of t to be equal to cosine t plus phi 0, comma sine t plus phi 0, for all t in R plus, right? This time dependent vector is written like this for all time in the positive real axis. Okay. Now note that in view of 35, in view of equation number 35, which was the initial condition, right? E equal to cosine phi 0 and Q is equal to sine phi 0. There exists a phi 0, so that the first component of the initial vector is cosine phi 0 and the second component, or the y component of the initial vector, is sine phi 0. So this was 35. So in view of this equation number 35, the function, this time dependent vector to be more precise, w is equal to w of t given in 37, satisfies the initial condition 34. The initial condition 34, right? Which is x0 is equal to p and y0 is equal to q, right? Because if you plug in 0 here, t to be 0 here, then you will get cosine phi 0, and cosine phi 0 by 35 is p, and you will get for the y component sine phi 0 at t equal to 0, and sine phi 0 is q, so that y at 0 is equal to q. Okay, so we are good with this time dependent vector. Writing x at time t as cosine t plus phi 0 and y at time t as sine t plus phi 0 for all time in the positive real axis. We compute that x prime of t is equal to minus sine t plus phi 0, which is nothing but y of t, and y prime of t is cosine t plus phi 0, which is x of t. They are both true as long as t is in the positive real axis. Okay. So that since xt squared plus yt squared is equal to 1 for all t in the positive real axis, we see that x equal to x of t and y equal to y of t, the system in 22. Okay, let us try to have a look at 22, which was what? So let me write down 22. Dx over dt is equal to minus y plus mu x, 1 minus x square minus y square, and dy over dt is equal to x plus and right, and you see that as x squared plus y squared is equal to 1, right? This is going to be satisfied because we have seen that x prime is minus yt, as we have here at x squared plus y squared is equal to 1, and y prime is equal to x whenever we have x squared plus y squared is equal to 1. Okay. Now, but uniqueness of the solution to the IDP22, by uniqueness of the solution to the IDP 22 and 34, which tells us that x at 0 is p and y at 0 is q, we have that w of t is equal to u sub p comma q at t for all t in R plus. Okay, so that the assertion in 36 follows. What was 36? The 36 was the assertion that u sub p comma q at t is cosine t plus phi 0 sine t plus phi 0. So we have therefore been able to show that the orbit of p comma q is the unit circle of radius 1 centered at 0 comma 0 if p comma q is in S1, that is p square plus q square is equal to 1. Okay, all right. Okay, now since S1 is a simple closed curve, one immediately sees that Okay, so since S1 is a simple closed curve, one immediately sees that S1 is a cycle, because S1 is an orbit and S1 is a simple closed curve, and hence S1 is a cycle of the system. S1 is a cycle of the system in 22, the governing equation, the governing ODE. Using the computations done in lecture 4, done in lecture 4, equation number 12, okay, for the system dx over dt is equal to minus y, and dy over dt over dt is equal to x, one immediately sees that in the present context, if P comma Q is in S1, then the alpha limit set of the orbit of PQ, which is S1 again, is equal to the omega limit set of the orbit of P comma Q is equal to S1 itself. Okay? Using the same computations, we can see that. So, hence we have been able to prove the following. We have been able to prove that if P comma Q is in the unit circle around the origin, then gamma sub P comma Q is the unit circle itself, and the alpha limit set of the underlying orbit is equal to the omega limit set of the underlying orbit is equal to the circle itself, the unit circle itself. Now, I will leave it as an exercise for you to check the following. One, if mu is negative in the system 22, okay, so if mu is negative in the system 22 and this vector PQ is in the open ball of radius 1 centered at the origin, set minus the origin, then the alpha limit set of the underlying orbit is the unit circle, where the unit circle. We all know that this is the collection of all the points of R2 such that x squared plus y squared is equal to 1. That is, S1 will be the alpha limit set of any orbit of P comma Q belonging to the open ball B1 0 0. That is this thing, right? PQ belongs to B1 0 0 set minus okay. Secondly, you have to show that if mu is negative in the system 22, and the point P comma Q is outside the closure of the open ball B100, that is E squared plus Q squared is strictly greater than 1, then the alpha limit set of the orbit of P comma Q is S1. These are the two things that you have to show using the techniques that we have learned so far. So I numbered them as 1 and 2. Given the fact that both 1 and 2 are satisfied, for the system 22, the cycle S1 which is the orbit for a point on the unit circle. Okay, and hence it's a cycle of the underlying dynamical system. The cycle S1 is called a limit cycle of the system 22, right? So it itself has to be an orbit for some point in the open set, and that has to be a non-self-intersecting closed curve. It has to be an orbit that is non-self-intersecting closed curve. Then we call it a cycle, right? So now we are going to close this lecture with the general definition of a limit cycle. Okay, but before that, I'm going to draw a picture for you for this system that we have seen already. So this is the limit cycle. The limit cycle is an orbit which is S1, which is the unit circle, right? The circle of radius 1 about 0, 0. Okay. So we have seen that if we choose the initial point satisfying the initial condition of the IDP to be strictly inside the open ball B100, right? If we choose the initial point to be strictly inside this ball, open ball, then as time progresses, the orbit, the trajectory is going to spiral down to the origin. Okay, we have seen this picture, something like this. Okay, and for this orbit, the alpha limit set is going to be the circle itself, right? And for the second point that you are supposed to prove, if you choose the initial point to be outside the open ball, the closure of the open ball, meaning that you have to be out of this closed ball, okay? And then if you are outside, then if you draw the orbit something like this, which will go away from this circle, you'll be able to see that for such an orbit, the alpha limit set will again be the unicircle that we are considering. Okay, so which means that for any point outside the cycle that we are considering, the alpha limit set is going to be the cycle, and for any point inside the open ball or inside the cycle that we are considering, the alpha limit set will be the cycle itself. Okay. And that's the concept of the limit cycle. Now let me give you the general definition of limit cycle. Definition: limit cycle. To close this fifth lecture, let U be an open subset of R to the n, and F be a vector field from the open set to R to the n, be a C1 vector field. We also want it to be C1, a differentiable vector field. A closed orbit, and by closed orbit we mean that the initial and final points are the same. Initial and final points are the same, or mathematically speaking, it's a map gamma from S1 to R to the n. Well, I don't write R to the n, the open set, because I want the closed orbit to be in the open set. So let's write it U in the lecture note as well. Gamma of the system, let me write down the system now. dx over dt is equal to f of x. Okay, is said to be a limit cycle. This closed orbit is said to be a limit cycle well, it is a closed orbit, and since it's a cycle, it's a non-self-intersecting closed orbit. A non-self-intersecting closed orbit. Okay. So a limit cycle of the system, this closed orbit is called a limit cycle of the system if there exists a neighborhood V gamma contained in the open set U, something like this. So in this case, S1 is the limit cycle, and this is the orbit, the closed orbit that we are considering. And so if I choose a point here, then I can draw a neighborhood of this point on the orbit gamma that is contained inside this open set U of R to the n, such that, okay, neighborhood V gamma of the orbit, sorry, I think I made a mistake here. So I have to take a neighborhood of the orbit, meaning that something like an annulus, like this, that will contain this circle, unit circle, okay? So I had to correct it in the lecture note as well. This is the neighborhood, okay? So this circle gamma is contained in this annulus, okay? And that annulus is going to be the neighborhood of gamma. So now, in our context, that is going to be the that neighborhood is going to be the annulus, okay? So now if you pick up such that for all P in this neighborhood V gamma, meaning that this is the annulus that contains this orbit gamma, and if you pick up a point anywhere from this neighborhood or from this annulus, okay, then either the omega limit set of the orbit of that point P in the neighborhood is going to be the orbit, it's the orbit or the cycle itself, or the alpha limit set of that orbit is going to be equal to the underlying orbit or the underlying cycle itself. that we have seen in our present context. Then we say that this closed orbit, which is also non-intersecting, is called the limit cycle of the system. Okay. Okay, I think we stop here. So we have closed the lecture by providing the general definition of a limit cycle. Thank you for attending the third segment of the fifth lecture.